Hello there, Mr. Sutton here, bringing you the AB Calculus 6-2 Extra Practice number 5 solutions on separable differential equations. On this problem, I'm trying to figure out what y equals, given this differential equation over here, and also this initial condition. We have basically 1, 1 as our initial condition. So since I have an output variable, y, in my differential equation, I can't just take the antiderivative right off the bat. I have to first separate my variables to get this stuff that has a y in it with the dy. Now this is a little bit tricky figuring out how to do this, but what we can do here is treat this whole 2 minus y thing as a factor and divide both sides by that. So I basically end up with dy over 2 minus y. Now you might wonder, well, what's left on the other side if you've done that? Well, you still have a 1 left over there. And then we have a dx getting multiplied by both sides, so we have 1 dx over there. Now we can take the antiderivative of each side. So on the left side we have ln absolute value of 2 minus y, but we have to also divide by -1, the derivative of this inner function here. So that's actually negative ln absolute value of 2 minus y over there. And on the right side, this is just going to be the antiderivative of 1 basically, which is x. And don't forget there's also a plus c over there. Now we have to find that c that we just added in there. To do that, we have to plug in our initial condition. So I have negative ln absolute value 2 minus the y value 1 equals x value of 1 plus c. And let's see here. This is ln of 1, which is just 0. So the whole left side is basically 0. Subtracting this 1 over here to get c by itself, we have c equals -1 then. And I'm about to plug that back into my general solution here. The problem, though, is I have this absolute value. I have to resolve that first. So looking at my initial condition, I see that y in the initial condition is 1. Well, if y equals 1, then the stuff inside here, 2 minus y, is going to be positive, which means that I don't really need the absolute value and I don't need to negate everything. I can just replace the absolute value with a parentheses. So I'm going to have negative ln parentheses 2 minus y equals x, and then we have to do the c value, so -1 after that. Almost there, but I have to isolate y first. So let me start by negating everything to get rid of the negative outside the ln. So I have ln of 2 minus y equals negative x plus 1 or 1 minus x, either of those. And then to get rid of the ln, I have to raise e to both sides. So that gives me 2 minus y equals e to the 1 minus x. And then there's a few other things I need to do here. I can subtract 2 from both sides. That gives me e to the 1 minus x minus 2. And then finally, divide both sides by -1. So I can write that as either negative e to the 1 minus x plus 2, or like they have in the answer choice, I can write that as 2 minus e to the 1 minus x, which is going to end up giving me, let's see here, that looks like answer choice. Wow, these all look so similar. We need 1 minus x, not x minus 1. So that would be answer choice B. A is pretty close, so be careful there. For this problem, we're told that f of x is a particular solution to this differential equation, and we have this initial condition of f of 1 equals 0. We want to know the value of f of -2. Now this is kind of interesting because this is a diffie-q problem where you have to find the particular solution and plug in the number, but they're also giving us the calculator here. As it turns out, we actually do need to use our diffie-q dance in order to do this. The calculator alone is not going to be enough, and if you look at the differential equation they give you, you see why. You might have been thinking, well, can't I just do my initial condition plus the integral of this stuff from 1 to -2. The problem here, though, is that you'll notice there's multiple variables in this derivative. We have specifically this output variable of y in there. So we can't just use the calculator FTC method. We have to actually figure out the particular solution to this thing. So let's go ahead and do that. Since I have a y here, an output variable in my equation, I have to separate my variables at the very beginning. So I'll get the y over here with the dy by multiplying both sides by e to the y. So I have e to the y dy on the left. And I need to get the dx over on the other side. So I'll have e to the x minus 1, all of that times dx. Now I'm going to take the antiderivative on each side. On the left side, this is just going to be e to the y, which works out pretty nicely. On the right side, we have e to the x minus x. Don't forget there's also a plus c over there. We have to go ahead and solve for c now. To do that, I plug in my initial condition of 1, 0. So I have e to the 0, plugging in that y value, equals e to the 1 minus the x value 1 plus c. E to the 0 is just 1. If I add this one over there, I end up with 2 on the left side, and then I can subtract e. So 2 minus e, or negative e plus 2, either of those is our c value. Now plugging this back in for c up here, I have e to the y equals e to the x minus x plus 2 minus e, all of that craziness. And then to get y by itself, which is what I actually need in order to get my f function, because f of x is really just the y that I'm trying to isolate here, I'm just going to take the ln of both sides. That pops the y out of the exponent on the left, and ln of e is just 1. On the right side, I have ln of all of this craziness. And at this point, it's now time for me to plug negative 2 into this expression. So here's what I've got going on my calculator. I've taken a moment to enter all of this stuff in my y1, and actually I should have done ln of all that stuff. So let me just go down to y2 and do ln, and then let me just do alpha trace y1. There we go. Problem solved. I could have just done ln of all this stuff originally, but I forgot. Easy fix, though. So at this point, let me quit out of here now, and I'm going to do alpha trace y2, because that's where I ended up storing the whole thing. y2 of, and now I need to plug negative 2 in there, so negative 2, and then just press enter and hope for the best. We get about 0.349 if I round off to 3 decimals, so that's going to be answer choice B. On this problem, I want the general solution to this differential equation. The key on this one is recognizing we have an output variable, y, in our differential equation, so I have to separate my variables before I can take the antiderivative. To do that, I'll multiply cosine of 4y by both sides. So we've got cosine of 4y dy on the left, and I'm also going to multiply dx to get it over on the right with the cosine of 8x. Now I can go ahead and take my antiderivative. So for this left side, antiderivative of cosine is sine, but we have to divide by this inner tail of 4 to offset the chain rule. So this is going to be 1/4 sine of 4y. And over on the right, same idea, we're going to have 1/8 sine of 8x. Don't forget to add the plus c in there. And I'm going to call this C1 for reasons you will see in a moment here. Now looking at the answer choices, it looks like all we actually have to do is isolate the c and basically get rid of the fractions. So to get the c by itself, I just have to subtract this 1/8 sine of 8x to the left side. And to get rid of the fractions, I'm just going to multiply by 8. That would get rid of both fractions. So when the dust settles, I have 2 sine of 4y minus, because we subtracted to get this second one over here, minus sine of 8x. All of that equals, well, I mean, I multiplied by 8, so this is no longer the same constant that was there, but it's some other constant, which I'll just call C2. It may not be the same C, but it's still a constant, so this works. So let's see what answer choice then we have to pick. We need 2 sine of 4y. The only answer choice that even has that is going to be C, and it has the rest of it too. So choice C. For this problem, I want the particular solution for this differential equation with the initial condition given here. To start getting started on this process, we have to notice that we have a y, an output variable, in the equation. So that means we have to separate our variables before taking the antiderivative. To do that, I'll just multiply 2y by both sides. That gives me 2y dy on the left. And now I'm going to multiply dx by both sides to get it on the other side, because I don't want it on the same side as the y stuff. So I have 3x squared minus 1 parentheses with a dx outside there. Now I can go ahead and take my antiderivatives. So I've got y squared on the left side. On the right side, this is going to be, let's see, this bumps up to a 3. Dividing by that, we have x cubed minus x plus c. And at this point, I need to find the c value by plugging in my initial condition. So on the left side, I've got the y value 4 being squared. And on the right side, all these x's are really the ones that we were plugging into the f function. So 1 cubed minus 1 is just 0. So you just have c on the right side. On the left side, we have 16. So c has a value of 16 then. Plugging that back into this plus c general solution we have up here. We have the beginnings of a solution. We're not quite there yet, though. We still need to actually take the square root of both sides to get y by itself. And when we're doing this, we have to be careful because you end up with a plus or minus square root. We have to pick one of those for the particular solution. So to make that decision, we see that we have a y value of 4 in the initial condition. Since y is 4, in general, y has to be a positive quantity. So that means when I take this square root, I have to write y equals the positive square root of x cubed minus x plus 16. And that is going to give us answer choice B. For this problem, we want the particular solution to this differential equation given the initial condition y of 0 equals 3. So to get started here, first off, we have to separate our variables because we have this y squared, this output variable, in the equation. So let me multiply y squared to both sides to get it over with the dy. And now we also have to move this dx over to the right side by multiplying. So we have 2x minus 1 quantity times dx. Now let's go ahead and take some antiderivatives. So on the left side, this is 1/3 y cubed. On the right side, going left to right, we've got x squared minus x plus c. And I'm going to go ahead and find c at this point by plugging in my initial condition. So I've got 1/3 times the y value 3 cubed equals, now we have the x's, we're just plugging in 0, which is really nice. So we just end up with c on the right side. So c is going to equal just whatever we have on the left side then, which is going to be 1/3 of 27, which is 9. So plugging 9 back in for c up in this equation we just wrote, we have a 1/3 y cubed equals x squared minus x plus 9. Not quite there yet, though. We still have to isolate y. So one step I need is multiplying everything by 3. That's 3x squared minus 3x plus 27. And then don't forget to cube root both sides to get y by itself. So we just have the cube root of all that craziness over there, which ends up being, I guess you could write this as the 1/3 power as well, and that would give us answer choice D. For this problem, we want to know the solution to this differential equation that has the initial condition p of 0 equals 4. Now, one way you could do this, since it's a multiple choice question, is you could take the derivatives of all of these to get a dp over dt, and then plug that in along with 4 for p to see what actually makes this equation come out true. However, this is possible to solve using the calculus techniques that we know and cherish. In order to do it, though, because you have this p in the equation, you're going to have to separate your variables. And in order to do that, it's going to help if we have just dp over dt by itself on one side and some other stuff on the other side. So my very first step here is going to be to subtract p to get it over with that 10. So 10 minus p. And again, I'm doing that because I just want to have dp over dt on one side. That's going to make it easier to get p's with dp's and t's with dt's by multiplying and dividing. So now to get p and the dp together, I have to actually divide both sides by 10 minus p, that whole thing. That gives me dp over 10 minus p. And on the right side, all that's left when you do that division is just a 1. So multiplying dt over there, we just end up with 1 dt, or just dt if you don't feel like writing the invisible 1. At this point, after that tricky first couple of steps, we're now ready to take the antiderivative on both sides. So on the left side, that's going to be ln of absolute value of 10 minus p, but we have to divide by this inner derivative of negative 1, so it's actually negative ln of that stuff. On the right side, we just have a t plus c. Don't forget the constant there. To figure out the value of c, which I'm going to need for this, I need to plug in my initial condition of 0, 4. So I've got a p-value of 4 that they're giving us in the initial condition. And the t-value here, the initial t-value is going to be 0. So we have 0 plus c. So c then is just going to equal the negative ln of 6, which is not going to require the absolute value anymore. All right. Now, before I go ahead and plug that c value back into this plus c general solution, I need to resolve this absolute value. I can't have an absolute value in my final answer, and if you look here, they don't have it in any of their answers. So to resolve that, I look back at my initial condition where I see that my p-value is 4. Well, if p is 4, then the stuff inside this absolute value, 10 minus p, 10 minus 4, is going to come out positive. Since that stuff's coming out positive with my initial condition, to get rid of the absolute value, I don't have to do anything special. I just have to replace it with a regular parentheses, and the positivity will take care of itself. So I can rewrite this as negative ln of parentheses 10 minus p equals t minus ln of 6. And at this point, it's all about isolating p. To start with that process, let me divide everything by negative 1. So we have ln of 10 minus p equals, you could either write negative t plus ln of 6 or ln of 6 minus t, either of those. At this point, now I have to raise e to both sides to get rid of this ln. So that's going to give me 10 minus p on the left side. On the right side, I've got e to the all of this. Now, one thing you can do, since you have e to the negative t plus ln of 6 up there, if you're wondering where this 6 came from, you could rewrite that as e to the negative t times e to the ln of 6, basically unadding the exponents by multiplying bases. And then e to the ln of 6 is where this 6 is going to come from. I just kind of simplified things and skipped a step while I did it. All right, we also can subtract 10 from both sides and divide by negative 1. So that's going to end up giving us, let's see, initially 6 minus 10, but then 10 minus 6 when we divide by negative 1. So 10 minus 6 e to the negative t. And then that's going to be answer choice C. Careful, because D is pretty close, but C is the one we want. For this problem, we have a large vat being initially filled with a saltwater solution. A solution with a higher concentration of salt flows into the vat, since solution flows out of the vat at the same rate. Okay. Number of pounds of salt in the vat at time t is modeled by the a function, which they're not giving us. They are giving us the derivative of a, though, which they're telling us equals 6 minus 0.02 times a, which is kind of interesting. So at time t, vat contains 50 pounds of salt. First task on all of this is to write an equation for the tangent line to a at time 10, and then use that to figure out approximately how many pounds of salt we have at time 12. All right, well, my general setup for this, using just my tangent line approximation formula, I'm going to have L of t equals a of 10 plus a prime of 10 times, and then we're going to do t minus 10. Basically, f of a plus f prime of a times x minus a sort of setup. So we need to figure out a of 10, for one thing. The good news is they actually told us that. They said at time 10, the vat contains 50 pounds of salt. They're basically saying a of 10 equals 50. We also need a prime of 10. Now, to get that, we need to use this dA over dt formula. That's a little tricky, though, because this thing, you'll notice, does not have a t for plugging stuff in. It has an a. So when you plug in 10 to the derivative of a, you actually have to plug in the a value, which is 50, for this a right here. So plugging in 50, because that's the a value that goes with the input of 10, this is going to be, well, let's see here. 0.02 is really 1/50th, you might know. So this is 6 minus 1/50th of 50, or 6 minus 1, which just comes out to 5. So putting all this together, we can write L of t equals 50 plus 5 times t minus 10. So there is one thing we had to do. They wanted the equation of a tangent line, and whoop, there it is. Next, we need to know the approximation for time 12 of the pounds of salt. So for that, we're going to just plug 12 into the equation we just wrote. So 50 plus 5 times 12 minus 10. And I notice I'm writing a of 12 is approximately equal to this. It's not equal to, it's approximately, because this is a tangent line approximation. Need to write the approximately equals to get full credit on this. You could actually just stick units on this, which is pounds, and call it a day, since this is all constants. But if you want to simplify it, 12 minus 10 is 2, times 5 is 10. 50 plus 10 gives us 60 pounds of salt. It's a whole lot of salt. For this piece of the problem, they want us to show that a of t equals 300 minus 250 e to the 0.2 minus 0.02t, say that 10 times fast, satisfies the differential equation dA over dt equals basically what they gave us up here, with the initial condition a of 10 equals 50, which in case you were wondering from part A, you could have looked ahead, I guess, and seen that that's pretty much what they were giving you here anyway. So there's two ways to do this. One way you could do this is you could solve this differential equation with this initial condition and show that it actually does come out to what they wrote here. And that's fine, that'll work. It'll take a while though. A quicker way to do this would just be to show that using this a of t function, a of 10 equals 50, and also that if you take the derivative of this thing, that's going to equal whatever you get when you plug this function into the 6 minus 0.02a part of the equation. So I'm going to do that second piece just to show you that. So let's start with a of 10 equals 50. Let's see if that's actually true. So we're going to do 300 minus 250 times e to the 0.2 minus 0.02 times 10. So we're just plugging 10 in at the very end there. Well, this is really 0.2 minus 0.2, just moving that decimal over. So this is all e to the 0. E to the 0 is 1. 250 times 1 is 250. So basically this is 300 minus 250, which all comes out to, this is the intermediate step there, all comes out to 50. So we've shown that a of 10 does in fact equal 50, and I just showed this extra step just so I'm not trying to do everything at once. I need this to be believable that all of this stuff equals 50. Moving on now, we're going to show that this differential equation is true. To do that, we're going to figure out what dA over dt looks like for this a of t that they've given us. We're going to see what 6 minus 0.02 times a looks like for this a value, and then we're going to show that those two things are the same expression. So dA over dt, just taking the derivative of this thing, we're going to need the chain rule on this. We have derivative of 300 is 0, derivative of negative 250 e to the something is negative 250 e to the something, times the derivative of the something. The something is just the linear function here with a derivative of negative 0.02. So we're multiplying by negative 0.02 here. Now if I actually multiply this out, again, 0.02 is really 1 over 50. Negatives cancel. We basically have 250 over 50, which just comes out to 5. So this ends up just being 5e to the 0.2 minus 0.02t. All right, so this is the expression we would like to get when we plug this a function into the second half of this differential equation. So now we're going to take a look at 6 minus 0.02a, and we're going to plug this function in for a right here. So again, I'm just taking the a function that they claim satisfies the equation and plugging it in for a. When I do that, I've got 6 minus, and now I have to distribute here. This is a 50th of 300, which is going to be 6. So we're doing 6 minus 6 plus, well, we already did 0.02 times 250e to all that stuff. It came out to 5e to all that stuff. So we're doing a plus 5e to all that stuff there. These 6's are going to cancel, leaving us with just 5e to the 0.2 minus 0.02t. Since the dA over dt and the 6 minus 0.02a come out to the same thing, we have just shown that this a of t does satisfy our differential equation. For this last part, the final boss battle of this question, they're saying the flow of the solution into the vat is stopped and the solution is drained. The depth in the vat is modeled by h, and the differential equation for h, not h itself, the differential equation for it is given right here. It's negative k times the square root of h. Well, this is kind of interesting because they're not really telling us what k is. It's just some constant, and we're going to have to find it later. So if the depth of the solution is 16 meters at time 0 and 4 meters at time 30, what is h in terms of k, h of t in terms of t? All right, so this is a Diffie-Q problem, but there's a little bit of a twist. So at some point, we are going to end up with some expression that we can plug a c value in for, but that expression is going to have this k still kind of hanging around, and then we're going to have to go back and figure out the value of k. But one step at a time here. Let's at least treat this like a normal Diffie-Q problem. Now, one thing we always look for is to see if the output variable is in the equation. And here we see the output variable, which is h, because it's dh over dt. H is in the numerator. We see that this output variable is in the equation, which tells me I'm going to need to separate my variables. So to do this, I'm going to divide both sides by radical h, which basically gives me dh times h to the negative 1/2 power. And I'm going to leave this negative k on the right side. I need to move the dt over to the right side, so I'm just going to multiply by dt, and it doesn't really matter if there's t's or not over here. The key is that we just don't want dt hanging out with the h's. Now I can take the antiderivative of both sides, since I only have h's over here and only t's over here, or at least no other variables. So on the left side, using the reverse power rule, this bumps up to a positive 1/2. Dividing by that, we're really multiplying by the reciprocal, 2. So that's going to be 2h to the 1/2. And on the right side, this is now going to be negative kt plus c. So we used our reverse line rule there. And at this point, I have to solve for c as best I can. So to do this, I'm going to use the initial condition here. And it seems like there's two initial conditions. We have the times 0 gives us back an output of 16, and time 30 gives us an output of 4. So you might be wondering, well, that's two different points that I could potentially plug in here for t and h. Which point do I use? Well, if you're trying to find c, it would be nice if there was no other letters left hanging around. So if we plug in 0 for the t value, that's going to get rid of this k, and we won't have to deal with k until later on. So I'm going to plug in 0 for t, and that means I'm going to have to plug in 16 for h to go with 0. So I've got 2 times the square root of 16, and then that's going to equal negative k times the input value of 0 plus c. So just as I predicted, 0 gets rid of my negative k there. So we just have c equaling whatever 2 radical 16 is. Well, that's just 2 times 4, which gives us 8. So our c value then is 8. Awesome. So let's plug that back in here. We have 2h to the 1/2 power equals negative kt plus 8. But we're still not quite there, because even if we isolate h, we still have this unknown k value hanging around, and pretty sure we're not allowed to just leave that as k. We have to figure out what k is. So this is where that other data point they gave us comes in. They told us that our solution was at 4 meters when time was 30. So now we can go back using this sort of particular solution. It is a particular solution, but we have this unknown constant in here. We can use this. We can plug in 30 for t now and plug in 4 for h. So we have 2 radical 4 equals negative 30 times, or negative 30k basically. So we've got, let's see, 2 times radical 4 is just going to be 4. So we have 4 equals negative 30k plus 8. Subtracting 8, that gives us negative 4 on the left. Negative 4 divided by negative 30, that reduces to 2/15. So that's our k value. We can now go back and plug in k right here to write 2 radical h equals negative 2/15 t plus 8. So we're looking good here. We only have 2 different variables, h and t. Those are the only 2 we wanted. We're still not quite there, though. This is the problem that never ends, right? Because we still need to isolate the h value. So to do that, I'm going to multiply, or actually divide, both sides by 2. So that gives me negative 1/15 t plus 4. And then finally, I just have to square both sides to get rid of the square root. So we have h equals all that stuff over there, quantity squared, and we are finally done.